Let me start over. I'll start with the linearity with the time shift to the correct direction. Okay, fresh start, linearity check. Still the same thing. We have A is random numbers, one random number. B is also a random number. XX1 is 1 times 100 random numbers. XX2 is also the same size vector of random numbers. All right. We combine these as a test vector and then feed through that system. Okay, so combined signal. I call it combined signal just for fun, CS. Combined signal is same as A8 times XX1 plus BB times XX2. So this is our combined signal, what we feed through that system. And this output is actually when we are basically moving the signal forward, we are adding zeros on the beginning. So we have a 0 and from X, N we take the rest. So this is shifting signal to later location, right? Am I correct? That way, not the previous way. So combined signal, and we feed through that the system which has system is the 4-point running average. And that one actually is y of n equals 1 over 4 times x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. Okay, better. And now the output for this input would be FCS, simply 1 over 4 times, okay, CS plus, okay, now time shift to later time. We leave one element out of the CS. That's the time shift to later time. 2 time step shift is simply from element 1 to 98. Okay, and then plus da da da. 3 points on the beginning, 1 to 97. All right. So this is the system output for combined inputs. There. Now we calculate the later part. So I have the fxx1. Basically the same thing, but instead of CS, I have xx1. Now I have calculated this part. Next, I will just calculate the output for the XX2 signal. There, system output for XX2. Now I combine combined output CS equals A8 times FXX1 plus B times FXX2. Better. Okay, that's the combined output, meaning the lower part. And now I can check if these are the same. Norm of CF minus F CF minus FCS. That's supposed to be 0 if this is a linear system. Yes, this is close enough to 0. Remember that machine epsilon is that 2.2 times e to minus 16, so this is 0. As 0 as this one, equally 0, which proves that this is a linear system. If this was a non-linear system, this would be remarkably different, meaning, say, at least 0.1 or so. Big difference on the magnitude. Okay, so next part is the causality. And for that one, I will just make the NN from minus, I will do actually something here. So I make this one also 100 points. 100 points around the 0. On both sides of the 0, well, about 50 points. And my test vector here is actually around n size of nn, still multiplied by double of nn is greater than 0, greater than equal to 0 actually. So our signal starts at origin. So stem of nn xx. There we go. So that's the origin, and that's where the signal starts. So now I'm calculating the output for the system, which would be F something. Okay, I start with the Fs. I calculate the Fxx. Just do some editing here. There, and XX. So that's the output of my signal test vector. Let me stem that one too. Okay, yeah, that looks quite funny. Haha, it looks like a little bit smoother version of the previous, but anyways, the biggest difference is that, well, the biggest thing is that there seems to be nothing on the left hand side. So now we can test it by saying norm of Fxx where indexes are less than 0. That's supposed to be 0. That's exactly 0. There's nothing on the output before the signal starts. Causal system. Good. So if this was something else than 0, then it would be non-causal. Good. And then the time shift invariance. again, basically what we need to test is to feed a system with and without time shift. So we actually feed the system with a test vector, delay that one with some arbitrary number delay, and then we have the system, system. That should be the same as moving this one on the other side. So let's first calculate the time shifted output. Okay. I will use that XX as my test vector. First, the time shifted output, or wait a minute. Let's calculate the output of time shifted put. Again, we need to do some time shifting. It doesn't actually matter how much we do it for this test. Usually one time step is already enough. If you do more time steps, then there's some artifacts that come out more stronger. So basically, for time shift check, you should not use the arbitrary numbers for testing. So if I add one value here on the beginning, we should actually take it out, not take that one into consideration on the testing, since this is something that I added myself. So XX from 1 to 99. Okay, that's the well, time shifted input FXX time shifted. That's the time shifted output, or that this is the output for time shifted input. Okay, there we go. Calculate that one. Good. So we have TS there on all of those occasions. Good, and then we calculate the time shifted output, which we actually already have the FXX with us, just time shift that one. So FXX, TS FXX equals, so we just do the same time shift in here, FXX 1 to 99. And we compare the later parts only, not the beginning, which has the artificial number, since that actually sometimes gives some trouble. So compare only the real parts of the signal, not the artificial parts. So we say take the FXXTS from 2 to 99 minus TS FXX2 to 99. Wait a minute, 100. Well, it doesn't make any difference. Let's do it this one. So we take a 1 point from each end. Since we are, in any case, we are calculating no norm. If this is 0, then this system was time shift invariant. And yes, this system is time shift invariant. Whoa, that took some effort. Okay, so basically, okay, these first three parts will take about 50%, at least 50% of the time of this exercise. The second part is somewhat easier. You will be starting from a system description, like, for example, let's make this simple system what we have had this far. 4-point running average. We could also do some feedback of it. Oops. Okay, 1/4, 1/4. And then just follow this system. So how to do the first part? Oops. No. Just put the gains back here. How to basically, I will modify also this system a little bit, just for fun. Just make one delay term here. All right, and put 0.4 here, and then we have 1, 2, 2, 1. How to determine the difference equation? You just need to follow the signal. That's all there is. So here we have x of n. After the delay, we have x of n minus 1 multiplied by 2. So here we have x of n plus 2 times x of n minus 1 plus, then again, x of n minus 2 goes here, and then multiplied by 2 going up, 2x of n minus 2, okay, plus that one, x n minus 3. Feedback part, start from here. Now you have y n minus 1 multiplied by 0.2 plus. Okay, that's the difference equation. Y n equals to that. The system coefficients from this. You first start by moving all the terms which has output to the left-hand side. You have y of n minus 0.4 times y of n minus 1, and then something. And then you have the right-hand side x of n plus 2x of n minus 1 plus 2x n minus 2 plus x n minus 3. Okay, now A's and B's. A's and B's. Okay, we have A0 is always the multiplying factor for yn. Almost always 1. This here is A1. Where are the A2 and A3? Well, they are zeros, plus 0 times y n minus 2 plus 0 times y n minus 3. So, but usually you don't need to care about those. Okay, only the non-zero terms, or if there was a non-zero term later on, then you need to describe all the terms there. Then the BB, this is B0, B1, B2, B3. So you need to just match the delay term multiplier for each of these parameters. Right. So first we have this y of n. The difference equation was x of n plus 2x n minus 1 plus 2x minus 2 plus x n minus 3 plus, and then it had plus 0.4 times y n minus 1, and then y n minus 1, which means the system coefficients now bb equals to vector 1, 2, 2, 1. AA equals vector 1 minus 0.4, and then 0 and 0. The trailing zeros you can leave out, but I will just leave them in there. It doesn't actually hurt at all to have those. Okay, these are the system coefficients which define the whole system. Starting from, let's see, zeros and poles. Z-plane, BBAA. Sorry. Zeros and poles. Simply just Z-plane gives you zeros and poles. Frequency response. Wait a minute. Zeros and poles. Then we have the stability. Okay, stability. Is this stable system? Yes. Poles are inside of the unit circle. Locations of zeros and poles. These are zeros. And poles are roots of the polynomial defined by vector A. Okay, 0, 0, 0.4. So double zero at the origin, and then single pole at the 0.4. Okay. Next step, let me take a quick look at what I'm asking here. System coefficient, zeros and poles, stability. Again, zeros and poles, the same. And okay, using this actually on the system coefficients to basically run some data through it. So I have a test vector XX. All right, I have test signal is XX. What is the output for the system which has these system coefficients? YY equals filter BB AA XX. That's it. So system, or actually, I know that this system actually is linear time invariant. So system in MATLAB is exactly the same as filter function. It has the filter coefficient so that the B, which is the forward term, goes first there. A as the feedback term goes second parameter, and then the input signal, and that's it. Let me stem plot NN and XX. Okay, output looks like that. Compared to sorry, it seems that my network is actually failing. I have lost this connection? Oh, great. Wired. Now it's back. Oh, great. So, comparing to the previous, I could actually have two different figures. Figure 2 and stem plot my NN and input signal there. All right. So this is the input signal, that is the output signal. So input. Hey, wait a minute. Why is input and output? Oh, sorry. Figure 1. Let's put the output actually on one of those. So this is the output signal for this input. So what you can say, it actually has less variability on the signal. So it seems that this system is a low pass filter. Those high frequent components have been lost on this one. That's the output. So it's smoother output. Good. So now I can do the second exercise. Yeah, linearity, causality, time invariant check. Then the playing with the system. So from flow chart, you define the difference equation. From difference equation, you transform that one into this a form that has all the output terms on the left-hand side, input terms on the right-hand side. You define these system coefficients. The system coefficients then define the whole system. These are zeros and poles, and then the system coefficients. What I could also calculate now is what is the impulse response, which is the third exercise. Impulse response. So I have that n, and I can do delta is simply same as on the first exercise. This is the discrete delta. So this is impulse function. That signal goes through the system. I get impulse response. Filter BB AA DD. By default. See, let me. Okay, stem. Wow. Another H. There. That's the impulse response. And what I need to do now, I know that this is how many? The okay, the last term is x n minus 3, so this is third order system, meaning that I need to check if there are any input after nn is greater than equal to 3. So basically what I can do, I can check if HH starting from index is greater than the order number, has any non-zero elements, meaning again on vector which has non-zero elements, I can check the normal fit. And definitely there is something after the order number delay, meaning that this is IIR system. On the other hand, I know it already since the I have non-zero poles. So this is IIR system. But okay, the ultimate test is this one. Run the impulse through the system and check if there are any non-zero elements after the order number delay. So that's the ultimate test. If that would be zero, then it's a finite impulse response system. If that is non-zero, then it's infinite impulse response systems. This is IIR system. Okay. And the next part, frequency response for the same system. I like to have always, when I have a system, some sampling rate also there for the system to make sense of the parameters. So BB, AA are the system coefficients, then basically 1024 points. This is, by the way, an old format for frequency response. I'm an old guy, so I use this one. So freq with these parameters, B, A are the system coefficients. This is a number of points where this frequency response is calculated. The Fs is the sampling rate. Wait a minute. There. That's the frequency response. So this is a low pass filter. So the low pass actually starts. I think the cutoff frequency is somewhere in here around 70, 80, 70 or 80 dB, 70 or 80 hertz, and then it goes down. This is the stop band, starts at around 100. Is it 100? Oh no, 300 hertz, and stop band attenuation is 40 dB. This is not unity gain system. Definitely not unity gain, because this has a gain of 20 decibels. But anyways, low pass. Okay. So low pass system with about 20 dB gain. Scaling this one to unity gain, we just need to multiply the system coefficients of numerator, or divide them basically. We divide the system coefficients of numerator with the maximum gain of the current. Then it comes down to 0 dB, meaning maximum gain of 1. So BB equals BB divided by maximum value of absolute value of frequency response. We can calculate it like that. We get rescaled system coefficients. Only numerator coefficients need to be rescaled. And when we do the frequency response again, now we have 0 dB gain maximum. And yeah, now it's a little bit easier to read. So actually it's minus 30 dB on the stop band attenuation, and yeah, stop band starts at 300 hertz, and around 70 or 80 we have 3 dB per point. Good. Let me take a quick look at what else there are to be done. All right, frequency group delay. Unity gain, scaling done. Then the spectrum of signals. Okay. Okay. So unity gain. Scaling done here. Then the group delay. Uh, Let me find some help. Help me. Group delay. So I just calculate group delay like that one. Good. So, BBA. I think that plots also something. Yes. So this is basically the group delay in samples. The system group delay in samples with a normalized frequency. So basically, on the passband, we have about 2.2 time step delay for those frequencies, and it drops down, let's see, around, okay, maybe 1.8 on the passband, and then on the stop band, you remember it was later there on the higher normalized frequencies, group delay is around 1.3 time steps. So there's a difference between the different frequencies when they come out from the system. Okay, that's the group delay. The last part would be calculating the spectrum, but I will leave that one to tomorrow morning. I will continue. So you can have some time to now start the second and third exercise if you wish. Okay, good. So I'll be hanging around here until 3 o'clock, and then I'll kick you up so you have some time to go to the next class. Good. Wow, that was a full day.